All right, hello everyone. Welcome to the third and final video for section 4.5. Finish up our studies of these different tests and what they tell us about the shape of a graph, and then finish this section by looking at how the graphs of the first and second derivatives are related to the graph of the function, a little bit more than we already have. Okay, so just a reminder of our two tests, the first derivative test and the second derivative test. Recall that in both, you have to find critical points of the function. You do that using the first derivative, but then to check whether or not those critical points represent local mins or local maxes, we just have discussed different ways that we can use the first derivative and the second derivative to figure that out. Now, I will say you have to know how to use both. However, as you've probably figured out, the second derivative test will often be easier. However, also note the second derivative test is only good for critical values where the first derivative equals 0. So if you have a critical value where the first derivative the critical value comes from a place where the first derivative is undefined, then you'd have to use the first derivative test. All right, so we're going to put this all together and also use this to talk about intervals over which a function is increasing or decreasing, or concave up and concave down. So here we have this function h of y equals y cubed, excuse me, minus 3y squared minus 9y minus 5, and we need to answer these questions. So first, we need to find the critical values. So as we were just discussing, we'll take the first derivative here. So h prime of y will be 3y squared minus 6y minus 9. And then in this case, there are going to be no values of y that make this undefined. So we're going to take that first derivative, set it equal to 0. I notice I can factor out a 3 here. So I have 3 times y squared minus 2y minus 3. It looks then like we can factor that to 0 equals 3 times y minus 3 times y plus 1. And then from that, we can get that our critical values are y equals 3 and negative 1. Okay. And now the second part of this asks us to use those values to find the intervals over which h of y is increasing and over which it's decreasing. Now recall that the first derivative can be a useful test for this, because a useful tool for this, because we know when the value of the first derivative is positive, that means the function's increasing, and when it's negative, we know it's decreasing, right? So what I'm going to do is use the sign chart here. So I'll draw out my number line, mark these two values, so negative 1 and 3. And I know at both of those, the value of the first derivative is 0. And then we'll test points to the left of negative 1, in between negative 1 and 3, and then greater than 3. So we could do, say, h prime, of, say, negative 2. All right, and when we do that, I'm plugging in my calculator here. I get positive 13. And since that's a value less than negative 1, I know that's the only point I need to check. So I know that for all values less than negative 1, the value of the first derivative is positive. I can then do h prime of a number between negative 1 and 3. I'm going to do 0. If I plug that in, looks like I'll get negative 9. So I know for all values between negative 1 and 3, the value of the first derivative is negative. And then pick a value bigger than 3, so I'll do h prime of 4. And if I do that, 3 times 4 squared minus 6 times 4 minus 9. I get positive 15. And so this is a plus here. All right. So now we can use this information to identify the intervals over which the function is increasing and decreasing. So note, if we're looking for where it is increasing, okay, so this is going to be values where the first derivative is equal or is positive, right? And so we see that's for all values less than -1 and bigger than 3. And note we don't include -1 or 3 at each of those points because there the value of the first derivative is 0. So we'll write our answers here in interval notation. So it looks like we're looking at -infinity to -1 to describe that first interval. And then we're going to union that with the second interval, which is 3 to positive infinity. Okay. And then for decreasing, as we've discussed, that's where the value of the first derivative is negative. So in this case, that's going to be these values in between -1 and 3, again, not including -1 and 3. So we know that that interval will be -1, 3. And I haven't used parentheses on those again because they are not included. All right. Cool. Second part of this then. We're asked to find the value of y for which the second derivative now is equal to 0. So we've already found the first derivative. And that was 3y squared minus 6y minus 9. So we'll take the derivative of that now to get the second derivative. So h double prime of y, let's see, I said 3y squared, so that's going to be 6y. We had minus 6y, so minus 6, and the derivative of the -9 is 0 there. So now we'll take that, set it equal to 0. So if 0 equals 6y minus 6, and when we solve that, looks like we would get y equals 1. Okay? And recall from our previous video that at this value where y equals 1, what we now know is that is what we call an inflection point, right? And we're going to do some double checking on this, but most likely that is a point where the concavity of the function changes from either concave down to concave up or vice versa. So I'm going to again create a number line here. I'm going to mark that value I have, the 1 right here. I know the value of the second derivative there is 0. Then I again want to check values on each side. So I'll do, say, h double prime of 0 is a value less than -1. See, that would be -6. Do h double prime of 2 is a number that is larger than 1. So it'd be 12 minus 6, so it's going to be +6. So we see that for values less than 1, the value of the second derivative is positive. For values greater than 1, or sorry, I said that backwards. For values less than 1, the value of the second derivative is negative. For values greater than 1, it is positive. And so then this is going to mean that for values less than 1, the concavity of the function is down. And for values greater than 1, the concavity will be up. So for concave up here, looks like we're looking at all values 1 and bigger. So it'll be 1 to positive infinity. And again, we're not going to include 1 because that's where the concavity changes. And then for concave down, Okay, that's going to be all the values less than 1. So we have negative infinity, comma, 1. All right. And there we go. All right. Now, last thing for this section, just talking about, again, making more connections between the graph of a function and the graph of its derivatives. And we looked at an example earlier in this section where we had the graph of a function, its first derivative and its second derivative. Now we're going to go about trying to actually sketch the first and second derivatives based on what we see in the function here. So I'm going to start with, this function is called h of x, so I'm going to start by trying to sketch h prime of x. And the first thing I'll do here is try to identify the zeros, or the places where the derivative is equal to 0. And recall, as we've been talking about, those would be critical points where we have local mins or local maxes, right? So we'd be looking at this point here, and this point here. So it looks like those occur at approximately -2, 1, and 4. All right, and I will tell you for this next part, there's a little bit of kind of guessing and approximation goes with it, but we should be able to more or less sketch a pretty accurate portrayal of the first derivative. So I noticed that, again, -2 right here is one of my local mins, or extrema, and I noticed that for values of the values of the function that are to the left of that, it is decreasing, which means in our derivative over here, those would be values where the derivative is going to be equal to 0, or less than 0, sorry. So that means that my output values should all be below the horizontal axis, so it looks something like this. And then between the values of -2 and 1, we see that the function is increasing there. Okay, like that. So that means that all of our values of our first derivative should be positive, so they should all be above the horizontal axis, so something like this, and they have to come back down to 0 at 1. And then again, between 1 and 4, the function is decreasing. So we see all the values should be below the horizontal axis, and then back at 4 we hit 0. And from 4 on, the function is increasing. So that means in our derivative over here, all the values should be positive. So we get something that looks like this, which hopefully makes sense because the graph of the function h here kind of looks like it'd be the shape of a quartic or a degree 4 polynomial. And what we got here for the first derivative is something that kind of looks like a degree 3 polynomial. All right, and let's try to sketch the graph of the second derivative now. And to start like we did in the last one, I want to mark where my zeros of this should be. And as we discussed, those would be inflection points of the graph, so we need to find those over here. And we know where the local mins and maxes are. And if you recall, generally, inflection points, values where the concavity changes, are in between those. So between -2 and 1, about halfway between that would be -0.5. So it looks like we'd have an inflection point, yeah, right about here. So at -0.5, so I'll mark that on our first derivative here. And then between 1 and 4, that would be at about 2.5, so right about here. So 2.5, like that. And then, so we know the value of the second derivative will be 0 at each of those. Let's now look at what happens in the graph over here with the concavity to the left and right and in between those. So we see that for values less than negative 0.5, it looks like it's got that up like a cup shape, so it's concave up, meaning the output values for the second derivative should be positives. Yeah, so it'd be something like this. And I didn't mean to do that as a highlighter. There we go. And then between negative 0.5 and 2.5, we see that we've got this down like a frown shape, so that would be our concave down, which means that the value of the second derivatives all need to be negative, so it'd be something all below the horizontal axis. And hitting back at 2.5, 0 at 2.5. And then for 2.5 and on, it looks like we've got this up like a cup shape. So concave up. So all the output values would be positive. So it'd be something like this. So it looks like we get kind of a parabola looking shape, which again, if our original function is something like a quartic or a degree 4 polynomial, the first derivative will be degree 3. Second derivative then would be a degree 2. All right, that's what I have for now. Thank you guys for watching.